All right, welcome everyone. I am so incredibly pumped to be your guide today as we dive into this explainer on the absolute magic of separating mixtures. Seriously, as a teacher, there is literally nothing cooler than taking something that seems, like pure magic and breaking down the brilliant step-by-step science behind it. We're going to look at the world a whole new way today, uncovering some amazing secrets hiding right in plain sight. So here is our game plan for today. We'll start with everyday mixture mysteries, then move on to Solute versus Solvent. After that, we'll hit the classroom mixing experiment, and finally wrap up with saving lives with separation. Let's kick things off with part 1, everyday mixture mysteries. Okay, so I want you to really look at the world around you, not just as a student, but like a true chemist. Have you ever actually stopped to think, how in the world do we get those sweet, bright white crystals of sugar from tall, green, fibrous sugarcane plants? Or maybe a bit more seriously, how do doctors find malaria hiding inside just a tiny little drop of blood? I know, they seem totally unrelated, right? But believe it or not, they share one incredibly powerful secret. It's crazy how we can bridge these two totally different worlds. Think about the farmers out in the field crushing sugarcane to extract juice, and then scientists in a high-tech lab testing samples. These transformations, whether it's getting that sugar for your morning cereal or testing blood to diagnose a patient, they're all made possible by some seriously clever separation techniques. We're essentially taking mixtures straight from nature and using science to pull out exactly what we need. Moving right along to section 2, Solute versus Solvent. Okay, before we tackle any more mysteries, we've got to lock in our science vocabulary. Think of a mixture kind of like a party. We've got two main characters, the solute and the solvent. The solute is the guest. It's the substance actually getting dissolved. The solvent, on the other hand, is the host of the party. It's the doer, the one putting in the work to do the dissolving. So if you stir some sugar into water, the sugar is our guest, the solute, and the water is the host, the solvent, doing all the heavy lifting. Now, you can't just cram a million guests into a tiny room and expect a good party, right? Getting the proportions right is absolutely crucial. And that brings us to concentration. Concentration is basically just the amount of solute dissolved in a given amount of solvent. For instance, if a farmer is spraying crops, they absolutely must mix the exact right concentration of pesticide into the water. Too little, the bugs win. Too much, they ruin the soil. Getting that proportion right changes the whole game. And this isn't just boring textbook theory. Concentration has real, literal, life-or-death consequences. Take the number 0.9%. In a hospital, a standard IV saline drip is exactly 0.9% mass by volume of regular old salt in water. That means exactly 0.9 grams of salt in every 100 milliliters of solution. But why that exact number? Well, it turns out that specific concentration perfectly matches the fluids already inside your blood, making it completely safe to rehydrate the human body. Just think about that. Getting the math right saves lives. Next up, section 3, the classroom mixing experiment. All right, vocabulary and math. Check. Now it's lab time. Go ahead and strap on those imaginary safety goggles. We're going to dive into the physical process of prepping a mixture. Imagine taking a spatula full of our solid solute and getting ready to mix it straight into our liquid solvent, which for us today is just water. It's a super simple action, but you'll see that the results can be wildly different depending on what's actually sitting on that spatula. Let's split the class up for this one. Half of you are Group A and the other half, you're Group B. Okay, Group A, your mission is to take your spatula, add some common salt to 50 milliliters of water, and give it a really good stir. Group B, your turn. You're going to take your spatula, add some chalk powder to your 50 milliliters of water, and stir it up. Notice what we did there? We have the exact same solvent, the water, but two totally different solutes. Okay, time for the big reveal. Group A, look at yours. The salt basically disappeared completely, right? It formed this perfectly uniform solution. But Group B, check out your beaker. That chalk powder is throwing a bit of a tantrum. Instead of disappearing, those chalk particles are suspended in the water, and eventually they just settle right at the bottom. Why? Well, because the properties of the solute completely dictate how it behaves with the host solvent. It's a great visual reminder that not all mixtures are created equal, which means we can't separate them all the same way. And that leads us to our final part, Section 4, Saving Lives with Separation. It's amazing to think that the basic science we just watched in those simple beakers is the exact foundation for some truly mind-blowing medical breakthroughs. I have to tell you about one of my absolute favorite inventions, the Paperfuge.
See, normally in a multi-million-dollar lab, separating blood components, like pulling the heavy red blood cells away from the lighter plasma, takes an incredibly expensive electric machine called a centrifuge. But what happens if you're in a place with zero electricity? Well, taking inspiration from a simple spinning string toy, scientists built this hand-powered device. By pulling the strings, they spin blood samples at unbelievably high speeds, separating the heavy and light stuff, just like a fancy lab machine. No electricity required.
Just think about the sheer impact of this. To quote the source material, this low-cost tool can help detect diseases like malaria and anemia in remote areas. I mean, wow. Just by understanding how heavy and light particles act inside a mixture and getting creative with basic separation principles, these innovators figured out how to provide critical medical care to people completely off the power grid. It is the perfect example of how foundational science literally translates into human survival. Well, that brings us to the end of our explainer today. We started our journey talking about everyday sugar and salt and ended up looking at life-saving medical devices. So, I want to leave you with this one big final challenge. How will you use the science of separation to invent a tool that changes the world? Start looking at your surroundings a little differently. Question how things are put together. And maybe even more importantly, think about how you could cleverly take them apart. Class dismissed. I absolutely cannot wait to see what you all come up with next.